Welcome to Daily Papers, the podcast where we break down fascinating new research papers without the jargon.
Today, we're looking at a paper that asks a question that seems, on the surface, pretty simple. If you scramble a list of things, and you tell an AI exactly how you scrambled it, can it put the list back in the right order?
Right. Imagine you have a shopping list. Milk, eggs, bread. You shuffle it up to get eggs, bread, milk. Then you tell a language model, okay, the first item is now the second is now the third, and the third is now the first. Here's the scrambled list. Give me the original. It sounds like a basic logic puzzle.
Exactly. This task is what the researchers call inverse permutation learning. And you'd think for a super powerful AI, this would be a piece of cake. But the title of this paper gives away the twist: the impossibility of inverse permutation learning in transformer models.
Impossibility is a strong word in computer science. It's not just saying AIs are bad at this, it's saying they fundamentally cannot do it. And this isn't just some abstract puzzle. It gets at a really important weakness in today's large language models.
It does. We want AIs to be reliable. If you ask a multiple choice question, the AI's answer shouldn't change just because you shuffled the options A, B, and C. If you give it a set of facts to reason with, the order of those facts shouldn't matter. But right now, it often does. The models are weirdly sensitive to the order of information.
This unscrambling task is a perfect way to test that underlying skill. If a model can't even reorder a list when you give it the instructions, how can you trust it to handle more complex ordering issues on its own?
So the researchers focused on a specific, very common type of AI architecture called a decoder-only transformer. This is the blueprint for many of the most famous models out there, like the GPT series. And they found that this specific architecture has a fundamental blind spot.
And that blind spot has a name: the causal attention mask. Let's try to break that down.
Okay, an analogy might help. Imagine you're reading a book, but you're only allowed to read from left to right, one word at a time. When you're on the 10th word of a sentence, you can remember the 9 words you've already read, but you are absolutely forbidden from peeking ahead to see the 11th word or the end of the sentence.
You can only see the past, not the future.
Precisely. That's what the causal attention mask does. When the model is generating its output, say, the first word of its answer, it could look at all of the input prompt. But as it continues generating the second, the third, and so on, it can only look back at what it has already written. It processes information in a strict, forward-moving timeline.
And now I see the problem. Let's go back to our scrambled list. Eggs, bread, milk. The original list was milk, eggs, bread. To produce the correct first word, milk, it needs to grab the last item from the scrambled list.
But when it's trying to decide on that very first word, the causal mask is blocking its view. It's trying to write the beginning of the answer, but the crucial information it needs is at the very end of the input sequence. It's like trying to summarize the ending of a movie when you've only seen the first scene.
It's a one-way street for information, and the task requires making a U-turn. The model is architecturally forbidden from doing what it needs to do. So it's not just hard, it is, as the paper says, impossible.
Okay, so that's the bad news. The model has a fundamental flaw. But the great thing about this paper is that it doesn't just stop there. It then tests this theory by showing 2 ways to make the impossible possible.
The first way is pretty straightforward. What if you just get rid of the thing causing the problem? You remove the causal attention mask.
Yep, this essentially changes the model's architecture. Instead of reading left to right, it's like letting the model read the entire scrambled list all at once, jumping back and forth as much as it wants, before it even starts to write the unscrambled version. It gets to see the whole picture.
And when they do that, it works perfectly. The model easily solves the unscrambling problem. This is great because it confirms that the causal mask really was the culprit. But you can't just go in and change the architecture of every major language model.
Right, which brings us to the second solution, which is much more surprising and honestly much cooler. You keep the exact same model, with its one-way vision flaw completely intact, but you just change the input a little bit.
How so?
You give the model some scratch tokens. Basically, you just add some blank space to the input, like giving it a little piece of scratch paper before you ask it to write the final answer.
So the input would be the scrambled list, the instructions, and then just a bunch of empty space for the model to think?
Exactly. And here's what happens. The model is still moving forward, left to right. It sees the scrambled list. Then, when it gets to the scratch paper section, it can use that space to copy over the information it needs from the end of the list. It's essentially writing itself a little note.
Oh, that's clever. So it copies the last item, milk, onto its scratch pad. Now that information is no longer at the end of the sequence, it's in the middle, in the model's own notes.
And when it finally comes time to generate the final answer, it just looks back at its scratch pad, sees milk, and writes it down as the first word. It has successfully moved information from the future to the past, all while following the left to right rule. It has created a workaround.
This sounds a lot like the chain of thought or let's think step by step prompting that we hear so much about.
That's the huge takeaway here. This paper provides a mechanical explanation for why that works. Asking a model to show its work isn't just a psychological trick. You are literally giving it scratch space to overcome an architectural limitation. It uses the thinking steps to shuffle information into an order it can use.
So the intermediate thinking tokens don't even need to be perfectly logical sentences. Their primary function might just be to act as a memory buffer, a scratch pad to get around that one-way information flow.
That's what the paper suggests. It's a really powerful insight. It shows that a task that seems impossible for a standard decoder-only model becomes trivial if you just give it a little space to think.
So to sum up, standard language models have a fundamental limitation that prevents them from looking ahead, which makes them fail at tasks that require reordering information.
But this isn't a dead end. We can either change the architecture to remove that limitation, or more elegantly, we can just give the existing models a scratch pad, which they can use to reorganize information for themselves.
It's a fantastic paper that takes a simple problem, reveals a deep truth about how these AIs work, and offers a clever solution that has real-world implications for how we interact with them.
A perfect example of how a seemingly impossible problem just needs a little bit of scratch paper to solve.